Hello, welcome everybody. Today I'm going to be talking about cosmic rays, their energy spectrum, and their theoretical upper energy limit known as the Greason-Zatsepin-Kuzmin limit. Alright, so what's the big deal? What are cosmic rays? Are they some sort of dangerous mystery particle? Cosmic rays are high-energy particles which strike the Earth from outer space. They are called cosmic rays because they were initially thought to be a type of photon. Astronomical phenomena such as supernova, active galactic nuclei, quasars, and gamma ray bursts have all been speculated to be the source of cosmic rays. Studies of high-energy cosmic rays tell us about the acceleration processes and the interstellar medium. Right, so what do we observe here on Earth? High-energy collisions in the upper atmosphere produce cascades of lighter particles. Pions and kaons are the first to be produced and decay to produce muons. The end result are muons and neutrinos, which are products of the decay chain of charged mesons. So our next question is, what is the energy spectrum of cosmic rays? The lower energy limit is 1 kiloelectronvolts, which corresponds to solar cosmic rays. The peak of the distribution is in the range of 100 megaelectronvolts to 1 gigaelectronvolt. The number of cosmic rays with energies beyond 1 gigaelectronvolt decreases by a factor of 50 for every factor of 10 increase in energy. Greason-Zatsepin-Kuzmin, known as the GZK threshold, is found to be around 10 to the 10 gigaelectronvolts. The highest energy cosmic rays detected was above 10 to the 11 gigaelectronvolts. So let's talk more about the Greason-Zatsepin-Kuzmin limit. The GZK threshold is a theoretical model for the upper limit of the energy of cosmic rays. This GZK limit is set by the slowing interactions of remnant cosmic ray photons from the Big Bang with the cosmic microwave background radiation over long distances. There has been much debate about the GZK cutoff limit. From the top plot, we see that the flux of cosmic rays events decreases as the energy of the cosmic rays increases. And from the bottom plot, we can see that approximately 20 cosmic ray events with energies between 10 to the 10 gigaelectronvolts and 10 to the 11 gigaelectronvolts have been detected. Abbasi et al. Suggests that they have found the first observation of the GZK suppression. Their high-resolution FlyEye, also known as HiRes experiment, has observed the GZK cutoff with a statistical significance of 5 standard deviations. The HiRes experiment consists of 2 detectors stationed located on the U.S. Army Dugway Providing Ground in Utah, and they are 2.6 kilometers apart. Each station is assembled from telescope modules pointing at different parts of the sky, and each telescope module collects and focuses UV light from air showers using a spherical mirror of 3.7 square meter effective area. They measured the flux of ultra-high energy cosmic rays with the fluorescence technique in the energy range of 10 to the 17.2 to above 10 to the 20.5 electron volts. Abbasi et al. Goes on to suggest that a measure of the significance of the break of the spectral index at 10 to the 19.8 electron volts can be made by comparing the actual number of events occurred above the break to the expected number for an unbroken spectrum. For the latter, they assume the power law of the middle segment to continue beyond the threshold. From the independent high-res exposures, with events seen by both detectors removed from high-res 1, they expect 43.2 events above 10 to the 19.8 electron volts from the extrapolation, whereas 13 events were actually found in the data. The Poisson probability for the observed deficit is 7 times 10 to the negative 8, which corresponds to 5.3 standard deviations. They therefore conclude that they have observed the GZK cutoff with a 5 standard deviation significance. Berezinski et al. Studied the decay of ultra-heavy and quasi-stable particles as a source of ultra-high energy cosmic rays. The observations of ultra-high energy cosmic rays reveal the prevalence of a new isotropic component at energies greater than or equal to 10 to the 10 gigaelectron volt. This component is thought to have an extragalactic origin since a galactic magnetic field cannot entropicize the particles of such energies produced by astronomical sources in the galaxy. They assume that the ultra-high energy cosmic ray spectrum has no GZK cutoff and is nearly isotropic. Their main assumption was that cold dark matter has a small admixture of long-lived supermassive X particles. They assume that the X is a neutral fermion which belongs to a representation of the special unitary 2 times the unitary 1 group. They also assumed that the stability of the X particle is protected by a discrete symmetry which is represented by all interactions except quantum gravity through wormhole effects. In other words, the X particle is very similar to a very heavy neutrino low with conserved quantity number R' being the discrete analog of R parity. Thus, one can assume that the decay of X particle occurs due to a dimension 5 operator inversely proportional to the Planck mass and additionally suppressed by a factor of e to the negative s, where s is the action of a wormhole which absorbs one R' charge. Let us now turn to the cosmological production of X particles with a mass greater than or equal to 10 to the 13 gigaelectron volts. Several mechanisms can be considered, including thermal production at the reheating stage, production through the decay of inflation field at the end of the preheating period following inflation, and through the decay of hybrid topological defects such as monopoles connected by strings or walls bound by strings. Since, apart from the very small scales, fluctuations grow identically in all components of cold dark matter, the fraction of X particles is expected to be the same in all structures. In particular, the fraction of X particles is the same in the halo of our galaxy as in extragalactic space. Thus, the halo density of X particles is enhanced in comparison with the extragalactic density. On the graph, we can see the predicted fluxes from decaying X particles. The flux shown on the graph were obtained from a dark matter halo with a radius of 100 kiloparsecs and a mass of the X particle of 10 to the 13 gigaelectron volts. The decay of these particles produce ultra-high energy cosmic rays whose flux is dominated by the halo component and therefore has no GZK cutoff. So, let's talk about some of the flaws in these papers. For our GZK suppression experiment, the measurements of cosmic ray flux requires a reliable determination of the detector aperture. Abbasi et al. Claims that the aperture of high-res detectors was calculated using full Monte Carlo simulation. However, without a reliable determination of the detector aperture, they do not have reliable results for high-energy cosmic ray detections. In addition, there are high levels of uncertainty related to the experiment. The main contributions to the systematic uncertainty in the energy scale include photomultiplier tube calibration, missing energy correction, and mean energy loss rate estimates. These results in a total energy scale uncertainty of 17% and a systematic uncertainty in the flux of 30%. Some of the flaws with our GZK without cutoff paper is that it is based upon some very large assumptions. The fraction of X particles is expected to be the same in all structures. It is the same in the halo of our galaxy as in extragalactic space. They had made the assumption that the spectrum of high-energy cosmic rays was isotropic. In addition, there were constraints on their method. The most stringent constraint comes from the electromagnetic cascade radiation. This is initiated by high-energy photons and electrons from pion decays and is developing due to the interaction with low-energy background photons. The other constraint comes from the observed fluxes of positrons and antipositrons in our galaxy and from the isotropic components of the radial flux. So, what is this cosmic ray riddle? There is evidence for and against the GZK cutoff. Observation tells us that there is suppression at 6 times 10 to the 10 gigaelectron volts, whereas theory tells us that there is no such suppression. Which do we choose to believe? Unless the experiment is somehow mistaken, the data doesn't lie. So if the data disagrees with predictions, guess what wins? Our cosmic ray mystery looks to be solved, as there is a stronger case for the GZK suppression.